Okay, what we want to talk about in this lecture is A to D conversion or analog to digital conversion, sometimes called an ADC. Um, this is done using electronic circuits that are specifically designed for this purpose. Many medical devices take in data as an analog signal and then convert it to a digital format. Now, more and more, um, we're starting to have actual digital type transducers. So the A to D conversion is in effect done within the transducer. But conventionally, you would acquire the data as an analog signal and then you would use an A to D converter. So, as an example, in a PC, you have an A to D converter and then a D to A converter. So, as this PC is recording my voice, it's doing an analog to digital conversion, and then as you listen to the recording of my voice, it's doing a digital to analog conversion, and these are both done here in the sound card. So USB compatible data transformation devices are readily available and offer a much greater flexibility than a traditional just computer sound card. So in an A to D conversion, an analog or continuous waveform is converted into a discrete waveform. And so you have some function x of t that's then converted to a series of discrete measures where your discrete variable is n. So you would have a discrete number of points as composed to a continuous line. And those are real numbers, and they're only defined at discrete positions in time, and they're also typically only defined at discrete levels. So these numbers are called samples. Discrete points in time are usually taken at regular intervals, and that's termed the sampling interval, T sub s. So then x of t becomes a series of numbers, and the signal becomes x of n, where n is 1, 2, 3, and so on, all the way up to some maximum. And 1, x of 1 would occur at 1 times the sampling time. X of 2 would occur at 2 times the sampling time. X of 3 at 3 times the sampling time, and so on. So n is literally your number of samples in a data set. So the sampling interval can also be defined by something referred to as the sampling frequency, which is just 1 over the sampling interval. So if we sample at t sub s seconds, and we do that for a total t sub t time, then we're going to get the number of points in our data record, capital N. So the relationship between the sample index and the time it was sampled can be determined as followed, where t is equal to n over f of s. So here's an example of a continuous signal. And then if you look based on digitization, here's an example of what the discrete signal looks like. So this grid over here is illustrating that we're sampling at specific times. But the other thing we're doing is we're only allowing our signal variable to take on distinct levels. So, for example, you can be 1 or 2 or 3, but you can't be 1.5 or 2.2 or 3.7. Those levels don't exist. So what the system's going to do on this continuous signal here is it's going to take whatever that is and it'll round it to the nearest even level. And so that's referred to as the quantization. So you have these discrete levels, quantization levels, and the signal will get rounded up or down to the nearest level. So rather than this continuous curve, then you have these distinct levels or quantum levels that are shown over here in the discrete signal. In addition to that, you're only sampling at very discrete times. So you sample at 0, and then you sample at 1, and notice how the jump then is immediate. So instead of this nice smooth transition from 0 to 1, you've sampled and held your value until you get to 1, and then you sample and you hold your value until you get to 2, and then you sample and you hold your value until you get to 3, and so on. So these look like little staircases, whereas these are nice smooth curves. But when we have a discrete time and a discrete level, that's information that's easy for the computer to store and manipulate. So here's an example where we want to generate a discrete 2 Hz sine wave using MATLAB. We want a sampling time of 0.01 seconds. We want to use enough points to make the sine wave 1 second long, and the total time should be 1 second. So we want to plot the result as a function of seconds and label the time axis correctly. So in this example, you're given the sample intervals and the total time. So that tells you the number of points you have. So what's our sampling time? Our sampling time is 0.01. Our total time is 1. So if we take our total time and we divide by our sampling time, we'll get the number of points that we'll have in that array. So in a lot of MATLAB problems, the number of points is arbitrary. And it's up to the user to define a reasonable value or a reasonable number of points. Typically in MATLAB, you can create variables. So here we've created a variable t, and we've defined it. This syntax means you're going to start it at 0, and you're going to end it at 1, and you're going to do it in increments of t sub s seconds. So this would be a line of code that would define to MATLAB how you want to set up your time vector. Why is that important? It's important because when you plot signals, you don't want to plot signals versus sample number. And MATLAB is going to automatically default to plotting versus sample number. So when you actually plot, you want to plot versus time. And so it's important for you to be able, in a given problem with a data set, to be able to plot that as time, not as n. So here's some code that does what we were asked to do. So this first line basically just clears and closes all previous things that were in MATLAB. And then we define our sampling time to be 0.01 seconds. So t sub s is equal to 0.01. The semicolon in MATLAB is used because MATLAB has an automatic echo. And if you don't use the semicolon, it will echo back to you the command. Then our total time is going to equal 1. Okay, f is equal to 2. Basically, we're defining the frequency of our sine wave here. It's going to be 2 Hertz. And then our time axis is going to run from 0 to 1 in increments of t sub s. So to create the sine wave, we just have the sine of 2 pi ft. So that's the sine of omega t, where f has already been defined. MATLAB recognizes pi as pi. And then notice here we're going to plot, and we're going to plot t comma x. So MATLAB, you enter the in this case, x is like the vertical variable and t is the horizontal variable. You enter the horizontal variable first and then the vertical variable. And then if you want to plot points instead of a continuous curve, you can use this .k command in quotations. So the .k is going to give us points. Then you can use the label command to label your axis, and you can use the Y label command to label your vertical axis. So let's look. And unfortunately, these results are not coming out super clear. I don't know. Doesn't really, they're here, but mine, let me adjust this brightness a little bit. It's just not giving you a great representation of what that MATLAB plot should look like. Okay, so the first thing that you need to do in here is be sure that you can do this using MATLAB. And I know that you can't see this super well, but notice here on the curvy part that these points kind of align really close together so you don't get too choppy. And then notice here on the sloping part that this is almost linear, so it wouldn't really look choppy anyway. But here it's important to have those points close enough together. If they aren't close enough together, then what happens is you really are getting this little staircasey kind of signal. Okay, this is what your actual points are. And this is just kind of like an interpretation. I mean, would be like your sine wave, and this would be where your actual samples fell. And so you can see that in between your sampling points, you're going to have some error. And that error occurs because um, you've had to quantize the signal. So in other words, you're not up here, you're down here. Okay? And so if you were to take the actual signal minus the error signal, you would get something that looked like this. And that's referred to as your quantization error. Um, and so the problem is that ends up looking a little bit like noise, um, because it's an error between your true signal and your quantized signal. So that slice size in volts is the voltage range of the converter divided by the number of discrete values. Um, so if you have some binary number that has, say, B accurate bits, then the number of non-zero values that you can have is 2 to the B minus 1. So let's say we have an 8-bit system. Then you have a value at 0, and then you have values all the way up to 2 to the 8 minus 1. And so those are the number of bits that you can have in your output. So if you want to know what the quantization size is, you would take your maximum voltage and you would divide it by the number of levels, and then that would give you your quantization size. So clearly, the higher the number of levels, then the smaller the quantization size, and so that would mean the smaller the quantization error. The advantage of having a lot of levels is that your discrete signal begins to look more and more like your analog signal, and the noise, due to the fact that you quantized, becomes less and less of an issue. The disadvantage is obviously the cost of the A to D converter, that the more number of bits you use, the more difficult it is the more expensive it can be. So this would be analogous, for example, to pixels on a camera. So obviously, if you have, a 10 megapixel camera, then that means the individual little pixels of your digital photo are so small that the eye can't necessarily resolve the difference between a continuous and a discrete photograph. So the more pixels you have in a picture, the more it looks like a true analog photograph. So the same is true of quantization levels. The more quantization levels you have in an A to D converter, then the more your discrete signal looks like your continuous signal. So, for example, the specifications of a 12-bit analog to digital converter advertises an accuracy of plus minus the least significant bit. So if we have a range of 0 to 10 volts, what's the resolution of that analog to digital converter in analog voltage? So if our input range is 10 volts, then we can figure out what the least significant bit means by taking 10 over 2 times the number of bits minus 1. So 10 over 2 to the 12th minus 1 is 10 over 4,095. So what that means is that each level of quantization represents 0.0024 volts. So the resolution would be plus or minus 0.0024 volts. Now, what do we mean by least significant bit? Really, that's just a fancy way of saying the smallest possible level that you can quantize. So out of the 10 volt measurement, you can quantize 0.0024. So this kind of gets into a practical application of something that I think confuses a lot of high school and undergraduate students, and that is this idea of significant digits. So we talk a lot about significant digits, and we try to explain to students how when you're talking about a voltage, you only want to give the answer in terms of significant digits. So in this particular example, this gives you a very good representation of what is meant by significant digits. If our physical system can only give us 0.0024 volts, there is no reason to have another decimal place here because it's not physically possible to resolve in this measurement. So that's just an example of something that I think, a good physical example of something that I think a lot of people kind of struggle with, especially, in some of your first science and engineering classes, that whole idea of significant digits. So typical converters usually use an 8, 12, or 16-bit output. Some very high-end converters will use 24 bits. Most biological signals don't have a sufficient signal-to-noise ratio to really justify a higher resolution. If you go with greater than a 16-bit converter, you're really just quantizing the noise and characterizing the noise. So there's not a lot of reason to necessarily do that. So, if you look in dB at those 4095 levels, then 20 log of 4095 is 72 dB, but most biological signals just have dynamic ranges that go between 40 and 50 dB and are usually closer to 30 dB. So a 12-bit converter is more than adequate. So once again, some of these concepts are more related to the actual measurement instrumentation and would be covered more in depth in a biomedical instrumentation course. But you kind of have to understand when you start working with biomedical signal processing, first of all, that you're working with a signal that has been converted to a discretized signal. So when you do things like take a Fourier transform or do other things to the signal, you're actually not working with a continuous signal, you're working with a discrete signal, and that's going to have implications. Okay, so we won't really talk about this much other than to say you can kind of determine the noise due to the quantization error, and then there's some additional practice in how to write a MATLAB program that evaluates the quantization error. So if we have a 4 Hz sine wave and it's in a 1,000-point array, so we have 1,000 points and our sample is 0.002. If we want to quantize this into a 6-bit binary number, that can be done using this routine quantization.m, where that's a file given by the textbook author. Signal in is the original signal, signal out is the quantized number, bits is the number of bits for quantization. So we can have an original signal and then we can have a quantized signal. We can find the noise by subtracting the original from the quantized. So here is the code that does that, and hopefully we're going to see some results. So the noise variance that's determined empirically is pretty close to the theoretical value. So the empirical calculations just done through that MATLAB program. The theoretical value is done through that formula that we saw on a previous slide. The other thing that happens when you sample is that you're sampling in discrete time points. So in addition to amplitude slicing or quantization, you also have sampling or specifically sampling at given times. So since the purpose of sampling is to produce an acceptable copy of the original waveform, then the question is, how well does your sample signal represent your original signal? And it really depends on what your sampling frequency was compared to the frequencies that your analog waveform contained. So there's a famous theorem called the Shannon sampling theorem. And it basically says what sampling frequency we should use when we want to assume that we have a simple waveform, a single sinusoid. What sampling frequency should we use to represent that? So Shannon states that any sinusoidal waveform can be uniquely reconstructed if it's sampled at least twice in one period. So if we know our range of frequencies, then the sampling frequency needs to be at least 2 times the greatest frequency in the signal. So here's an example of 2 points defining a sine wave. So if we look at this signal, and we see that we've sampled it in these 2 points. There are signals with higher frequencies that contain those 2 points. But if we had a lower frequency, in other words, a slower sine wave, those 2 points would not be on the curve. So no sine waves at a lower frequency could pass through these 2 points. So this lowest frequency sine wave is uniquely defined. But there are pretty much an infinite number of higher frequency sine waves that could pass through these 2 points. So the problem is, okay, if you sample at a low frequency and you have higher frequency sine waves present in your signal, you don't know whether it's this one or this one. And when you filter, you can get these random higher frequency components, or when you sample, you can get these random higher frequency components that are introduced in an unusual way because you didn't sample at a high enough rate. So for example, if I had sampled at this rate, then I would uniquely represent this waveform. This one would not be, it would be too slow, so it wouldn't be uniquely represented. And as long as I didn't have anything higher than this waveform, if I decrease my sampling rate to roughly 0.1 seconds, then I would be able to represent this higher frequency waveform in a unique way, which now I cannot do. So Shannon's theorem can be described in terms of signal frequencies. Basically, sampling has a strange effect on the frequency characteristics. The sample signal spectrum, or distribution in frequency space, contains a mirror image of the original signal that's reflected around a frequency that's half the sampling frequency. So if our sampling frequency is Fs, then the spectrum above Fs over 2 is the mirror image below Fs over 2. So what this is really doing is this is shifting the signal spectrum in multiples of Fs. So let me show you a picture of that. So here's our continuous signal spectrum. If we now sample this signal, then what we're going to get is we're going to get that signal repeated with each sampling period, or with an integer multiple of each sampling frequency reflected. So now you can see, okay, if these two groups of spectra are too close together, these points and these points overlap. So you need to be sure that your sampling frequency is such that is big enough so that you spread these spectra out so that the components don't overlap. Otherwise, you're going to pick up this component here on this side of the spectra, and then there's some confusion of whether it's part of the lower frequency part of the one centered about 0, or part of the higher frequency part about this one. And so that's why Fs has to be big enough. So that this just kind of repeats that here, that these components here don't overlap with components on the other side. If they do, that's referred to as aliasing. And so what it looks like then is, as this group of frequencies gets closer to this group of frequencies and they start to overlap, you have this aliasing problem that makes it look like you have new components that are appearing that aren't really there. So it is important then to always sample at the Nyquist frequency. So if you have a signal, you want to know what is the highest frequency contained in that signal. You then double that amount, and that is your minimum sampling frequency that will represent the signal appropriately. So if you're looking at someone's EEG and there are components in the EEG at 150 hertz, then to adequately represent the EEG, you would need to sample at least 300 samples per second. Otherwise, you wouldn't represent the higher frequency components and you would create an aliasing problem. So that is why it is important to filter the noise, the higher frequency noise, out of the signal before you sample. So if you filter before, if you have an analog filter stage that does some pre-filtering before you digitize, then you do away with this issue, especially if you're limited in how rapidly you can sample. So the higher the sampling frequency, notice the greater separation of these components, the less likely you are to have problems with overlapping. The final thing to talk about when thinking about sampling is to realize that real data is not like an actual signal. An actual signal that we would analyze using, say, Fourier analysis, we sort of assume ranges from negative infinity to infinity. In our real world system, we have a starting and stopping point for when we record signals. And so what that looks like is, there's like a sharp discontinuity between beginning and end. And so that doesn't, rather than looking like the shape of the signal, it looks like the shape of the signal multiplied by a rectangular window. So there are a couple of strategies for how you can extend the data beyond what you can just store in memory. One is to zero pad. So in other words, here's our signal. We're going to add some zeros at the beginning and at the end. And that has the effect of slightly minimizing the fact that you would start out at this point right here. And so then it becomes kind of unclear where the zero level is in the data. Another is to do a periodic extension. So in other words, we take the end of this waveform and we add it to the beginning, and we take the beginning and we add it to the end, so that it looks like this waveform is repeating itself over and over again, which then gives you more of a look like it is a periodic signal. And the other is a symmetric extension, which takes this early portion of the waveform and reflects it backwards, and takes the ending waveform and reflects it forward. And sometimes you will do that to minimize abrupt discontinuities in the data points at the end of the data record. So you notice here at n equals 20, in these first two examples, we have this abrupt jump in value between 20 and 21 that's actually not physically real. So if we do this symmetric extension, that smooths out the change that occurs at some data points at the beginning and end of the data set. There are some other ways to do this that are actually a little bit better and a little bit more common, and that is the application of various types of windows after you do this, but that gets into a little bit beyond what we want to cover in this lecture today. So that would be the digitization and quantization part of the signal processing system. Because this is just a single slide, I'll just talk really briefly about buffering and real-time data processing. Buffer means you have a set of memory locations that temporarily store incoming data. So when you're acquiring data in real time, that's a little bit different because you can't really save it and do after the fact calculations. You want your calculations done in real time, but you can't really do real time calculations because in real time, technically you've only got one data point. So you use a buffer that kind of gets a short history, and then you can take the data that are stored in that temporary memory and do a calculation and then do whatever you choose to do with your calculation. So the buffer is continually filling and emptying, and often you'll have multiple buffers that fill and empty with some offset. So incoming data are used, say, and sent to two different memory arrays. And then that way, the one that's not being filled is processed and the one that's being filled is being filled. So you can also, have multiple buffers so that some are writing to memory while others are acquiring. So buffering is almost ubiquitous now in all digital data acquisition processing systems.